Hi, good morning and welcome to the ZP Developer Zone. So we like to do this Developer Zone every week, and it's really answering technical questions that have come in during the week. I'm in a really bad place when it comes to internet connection this week. If you sort of can look behind me, you can see I'm obviously in a hotel. So I spent 20 hours yesterday getting here, and the internet is absolutely terrible. But that said, I will obviously go forward. You know, these technical questions come in. I will try and do a little bit of a demo on a new, I'm sorry that my screen's so bright there, but we have the Sense It All platform. The Sense It All platform is really both a Potentiostat and it's a MVP. You can call that a sort of minimum viable product or prototype depending on the whole system, let's say, but we can put sensors on it, and I'll be talking about lead in particular today. If you're used to this technology, then you'll understand that it's kind of QR code driven. I'm actually just going to make Bluetooth connection with that device, which I've now just done, and all that will become a little bit clearer shortly. Let me just jump forward a little bit bit faster. So today's the 13th of October 2024. As I say, it's not the world's best internet connection, but let's look at the questions today. So I'm going to be talking about lead detection in a sample. I'll also be talking about potassium detection in sweat. We do get a lot of inquiries around potassium sensing in sweat. I mean, at ZP we have a sweat patch, we have electronics, we have we have potassium sensors, we have calibration solutions, we have rinse solutions. So we have everything. If you want to get to kind of a proof of principle, let's say in a laboratory setting. I'll just talk very quickly about the Sense It All versus AnaPot. I also appreciate that possibly the sound quality is not that best good today. As I say, I'm away in this kind of hotel setting. I will talk about pH sensors and electronics. Somebody has some pH sensors from ZP, so they're both curious about the impedance of those pH sensors, and they're also curious about how to drive those sensors with electronics. We actually have a single-purpose biosensor circuit, which is the only one I can recommend, but I'll also talk about some open source platforms as well. They've also asked about the impedance of their pH sensors. Their pH sensors actually are a little bit similar to these. The conductive tracks in these kind of pH sensors have sort of ohmic or single unit ohmic type resistances, but it's actually the impedance through the solution which is the highest, which is probably in the range of about 500 ohms. And I'll touch upon that as I go through. Lots of people are interested in lots of times doing multi-analyte detection, and if you're going to do STs, sexually transmitted diseases, then these are often, unfortunately, with sexually transmitted diseases, if one person's got one disease, they've probably got another two or three. So you can't just, if you're testing somebody for their sexual health, you end up having to do a panel of these things. Measuring the pH of pharmaceuticals, I will touch upon that as well. And just FYI, pharmaceuticals, when they are fabricated, they can have unique formulations. There's not one sort of generic formulation for all pharmaceuticals. This means that they may have different content in the what's called the excipients, and those different content can end up extracting materials at different materials at different rates. So just FYI, you can't make a blanket statement on whether something is extractable or not extractable by a pharmaceutical solution. You have to do it. I was thinking about this just a few minutes ago, and I was thinking the biggest thing when we're doing submissions sometimes in medical devices, medical diagnostics, is actually proving it's safe. And so extracting materials is a proof of whether something is safe or not. And so when you look at the cost of getting this kind of technology to market, actually a lot of that cost is, it's partly around performance, but it's also a large part around safety. So I cannot make safety statements, let's say through a YouTube video. You have to do the work, but I'll come to that shortly. When I say you have to do the work, you have to literally do that science and actually work out what is extracting, and does it extract into your solution. So I can't make a blanket statement on that, but I'll go into that a little bit. So I think a large part of today we'll be talking about a new assay that we've delivered for on the Sense It All platform. I've got the Sense It All in front of me at the moment, and in fact, at the moment, I've actually got it on the lead sensor. It's in Bluetooth connection with the Sensor platform, and I will just answer the questions, but just to say I do have it in front of me. Actually, this may become relevant in a minute. Well, it will become relevant in a minute. I actually got a soil sample here. So at ZP, when we're developing technologies, let's say we've made an assay for the detection of lead, sometimes we almost don't care about the sample. Now, the reason I bring that up is because this is for a different reason. I just happen to have it with me. This is 0.1 grams of soil in 900 milliliters of buffer. That means I don't really care what that soil is, because in fact 90% of this is my buffer. And so understand that, when questions like what's your pH, what's your salinity, what is your soil, I don't care, because 90% of it is actually coming from our buffer, and we do that so that we can become sample independent. That will become a little bit clearer actually as I go through now. So the questions are, is a dilution always needed? So this person's, or who's asking this question, is going to get one of the first releases of this new lead sensing technology. Is a dilution always needed? We only do it so that we can control things like pH. So if your sample has a pH of 7 or a pH of 4 or pH of 9, we don't care, because we do a 1 in 10 dilution. So that actually makes us pH independent. So do you always need it? No. And once you get this technology, you'll realize that actually it's quite open. And it's open through what's called the Julie backend. And I'm trying to demonstrate that today. The reason being is that, though I use the word trying, is just because the internet connection here is 5 megabits per second upload speed and download speed. Absolutely terrible, but I'll try it. So you don't always have to dilute, but you do always have to answer the question from sample to sample, if you're not doing dilution, that is, and this is generally my case as well. From sample to sample, will you always have the same pH? Will you always have the same electrolyte concentration? Will you have a large amount of solids that would otherwise need to be dissolved? So there's all sorts, or diluted rather, not dissolved. So when we dominate any sample by 90%, because we do a 1 in 10 dilution, lots of those problems just got reduced by about an order of magnitude. So you can see why we do, well, that's why we do what we do. It makes us incredibly generic, in fact. What I mean by this is, if somebody came to us and said, oh, will your lead sensor work in my water sample? I could actually answer is yes. Now, how could I answer that question as yes? Because, here's a water sample, for example. Well, of course, if I take 1 volume of that and dilute it in 9 volumes of buffer, then I've added all the pH, all the right pH I need. I've added the right number of salts that I need. I can do it. If somebody else came to me and said, "Oh, I've got a really muddy sample. Is it? Will your lead sensors work in that?" Well, of course, I can answer that with some degree of certainty, because I will take 1 volume of their sample, put 9 volumes of our buffer in it, so I dominate 90% of that sample. So the answer should be yes. In fact, we should be able to detect it. In fact, you can see what this does. This is a very different type of sample, very cloudy, full of bits, let's say. By the time I do a 1 in 10 dilution, same sample looks like this, much clearer, much more standardized. So if Zimmer and Peacock does a dilution in an assay that we may have delivered to you in the first instance, it's so that we can make that overall assay more generic. If you want to tweak it, absolutely can. Now, if you tweak it yourself, that's almost free, and as long as you understand how to do it. If you get ZP to tweak something, then that will end up costing money. But I can then make those statements like, in fact, this would work in fresh water, this would work in well water, this would work in seawater, this would work in brackish water. How can I make those statements? Because, in fact, we do a 1 in 10 dilution. Somebody's very interested in actually having a 2 ppb limit of detection. Of course, when we do a 1 in 10 dilution, we end up, essentially, if a sample is really 20 ppb, we end up diluting it to 2 ppb. So in that case, you would actually argue that the limit of detection is not really 2 ppb, it's actually 20 ppb, because we do a 1 in 10 dilution. But just remember that we do a dilution to make ourselves generic if you focus in on a particular application like mine water, well water, fresh water, seawater, you can simplify that workflow. Because in fact, seawater I think is possibly the easiest one, because seawater will always have a certain amount of electrolyte in it. So if you're interested in measuring lead in seawater, you can always argue to yourself that seawater will have about 35,000 ppm of chloride in that sample, so you don't need the electrolyte. I think seawater actually has quite a stable pH. I want to be a little bit careful on that statement. So I could quite easily seeing a seawater sample, take the seawater, put 50 microliters onto the sensor and get a result. No need for dilution, no need for sample prep. Of course, if you're then facing something like well water, I should say mining water. So if I was dealing with mining water from Australia, or mining water from Peru, or mining water from North America, I could quite easily see that mining water would actually be reflecting the local geography. So there, I can't make those blanket statements. So if I want to have a generic sensor for dealing with, I actually think I just listed out 3 continents there, I can see myself having to do that dilution, because I can't guarantee the composition of that sample between those 3 continents. So that's a place where I would actually always argue that I'd be doing that dilution. The dilution is not intrinsically required. It's so that we can normalize the sample. Just FYI, when we were calibrating and testing this system, we were working at 2 ppb, 5 ppb, 10, 50, 100, 150, 200 ppb. The reason I bring this up is because if you get a lead assay from Zimmer and Peacock, the workflow, and I've got some better slides on this, is take one volume of your sample, put 9 volumes of our buffer in it. That forgives all the variabilities that your sample may have, and we can then test it. I can understand if you want a simpler workflow, you are the only person who really knows your sample and how variable your sample will be. You can change that ratio, and you will actually see the platform is, when I say that ratio, that dilution ratio, you may even be able to eliminate it. But you will have to either engage Zimmer and Peacock to do that science, which will cost, or do the science yourself, because the platform is quite open as well. So you will not always have to acidify samples, FYI. Why do we do it? We do it because we just want to take pH as a variable out of the matrix. We've now got it on the app, the Sense It All app. In fact, I've got it open on my phone at the moment. What's the last question here? So yeah, for example, let's say you were, I think this would work particularly well. Let's say you were working with mine water. Mine water tailings tend to be a little bit acidic. So you may actually be working with a mining company who wants to test for heavy metal, release from their mines. You may not have to actually use any kind of sample prep in that case, because the mine water is brackish enough, which means it may have enough electrolytes in it. It may have a fairly fixed pH, and it may also be at a good pH, let's say. Now, as a business model, there's no harm in actually you charging people who otherwise want to use your technology to optimize it for their particular sample type. If they don't want to pay for that, then you can actually follow, the strategy that we use, which is we're doing a 1 in 10 dilution at the moment, and therefore, it again takes out all the variabilities between different samples. It will therefore affect that limit of detection, but it does make the applicability across many regions much easier when you do the 1 in 10 dilution. The electrodes can really be used with any pH. So you understand that if we do a 1 in 10 dilution, the pH of that solution is actually dominated by us. So I don't really care if people come in with, pH 5, 6, 7. I don't mind, because in fact it'll always be at the pH that we really dictate through the dilution. There's not really any conditioning of the electrodes. This comment is I think because people who are used to working with academic screen printed electrodes or stuff like that end up having to do a lot of conditioning of electrodes. At Zimmer Peacock, we try to make quick and easy assays. We don't try to build assays that require lots of conditioning. It's just not the way we think. It's not our philosophy. Anyone who knows me knows that I have a long experience in medical diagnostics, and started my career at making blood glucose strips. So I just conditioning and doing lots of, even the dilution in this particular assay is not something I'd really want to do. The reason you don't do dilution just out of interest in blood, in blood glucose, is because blood is actually reproducible enough that you don't have to do it. It's got, a fixed pH, and it's got the right number of, let's say, it's got a good number of electrolytes in it. Just out of interest, before blood glucose measurements became electrochemical, they used to be optical, and actually there they would actually do a dilution of the sample. You can extend to be doing other other methods at the same time. So this app has been developed to do lead. Can it do lead and copper? Yes, with the right kind of science, you could probably do lead and copper at the same time. We just, in this release, have not done it. I know that one of our engineers may have said something slightly different to this particular inquirer, but realistically, this is using anodic stripping voltammetry. So you can quite imagine that copper and lead, for example, will come off at different potentials, different stripping potentials, and therefore you can actually extend it. But that requires funding. I think we will at some point do copper because we've already kind of done a lot of work on copper already. So question number one, why do we do this dilution? We do it to forgive a bunch of sins that would otherwise come from the sample. So we'll take one volume of it. This means that we don't care if that sample is soil, we don't care if it's urine, we don't care if it's blood, we don't care if it's fresh water, we don't care if it's seawater, we don't care if it's brackish water. Why? Because in fact you do this 1 in 10 dilution. I put and I put vortexing here. The reason I put vortexing is because sometimes I've got a soil sample here, for example. This actually, you've got to think about the sample prep of the soil sample. That might be some extraction. With things like seawater, mining water, fresh water, everything's already dissolved, so it's probably just enough to actually shake it. You can now get this app, this by scanning the QR code through the app. It will wake up. In fact, I might do a quick demonstration for you now. As I say, in fact, what I'll do is I'll do a sample. I'm a little bit cautious on the internet connection today, but just bear with me whilst I do a quick demonstration. So I'm actually going to do, let me just do this, right. I'm just going to change the target to something I'm much more familiar with, because I'm a little bit, I've got it in lead mode at the moment, but the workflows are actually all quite similar, and it's really the back end that I actually want to show. So I'm just going to get my, sample, in fact, and I'm sorry about you can appreciate I'm not in my normal place, but I'm in Bluetooth connection with my device. I've got a sensor on there. I'm just going to grab a pipette. Why do we love electrochemistry? Because it really allows, this is not the world's best looking sample. In fact, this is actually quite cloudy and turbid. This would actually really fox or confuse a lot of optical measurements. But electrochemistry is quite a robust science. Now this won't be great. The reason it won't be great is because the internet connection here is so poor. But in fact, I'm just going to give this a name, which I will do now. I know a lot of this is actually off the screen. It's a bit bright, but my apologies for that. All right. So the app is now running. I'm getting raw signal, let's say, in real time as that runs. But don't worry about that when I say that kind of thing, because in fact we do turn the raw signal into a meaningful number, let's say, for the clients. Now what I'm going to do is I'm just going to, in fact, so it has run that assay, which is good. I'm going to share my screen. I say it very deliberately because I'm having to do it in the, it says upload complete. It's all a bit bright on the screen, but this is the beauty of the technology. I want to say I'm probably pretty fortunate actually, because like I say, it's such a poor internet connection at this place that I'm lucky to kind of even to get. So every time we do an assay, the assay automatically goes to the cloud. So this is the assay that I just done, just ran rather, I can see in this particular case, my voltammetry. But if you do your lead assay, understand that there's a lot of transparency in what's going on here. So you'll come into Tools, you'll be able to look at the raw data. This, in this particular case, is my first scan, this is my second scan. And I can see here, in this particular case, the low pass filter was used. I can see the window of analysis that I used. That's really important. Start getting a sense of actually, you know, in the lead assay, if there's a stripping peak, we're actually able to modify where the software is actually looking for that stripping peak. So if you come up with different samples with different pHs, for example, even different chelating ion or different chelating ligands in that solution, we can change the window of analysis. But we open up a window, we tell it where to center the analysis, we tell it how to do the conversion of signal into calibration. So here we're doing logarithmic, and we've got a formula here. Here we've got dilution factor. So just FYI, if you change pH, for example, or don't do dilution, it will change the signal. But we can go in the back end of Julie and shift where we look for the signal. We can go in the back end of Julie and actually look at how to turn peak height or area under curve into a concentration, because now it's a very different type of sample with a very different calibration factor. Just know, if we go from dilution of 1 to 10 to 100, no sweat, it can all go in there. So it's to say that if you're using the lead system from Zimmer & Peacock, it may come in a default way of working. But in fact, if you come to us and somebody else comes to us and says, I want to do lead in the blood of children in North America, because I think that's actually something that's not needed, sorry, it may be even mandatory, we can do that. But that will require, you know, it's a different sample, it's probably not require dilution, but we can just change how to turn raw signal into final concentration in the back end through the Julie system. So it's not the big engineering lift that you would otherwise have imagined. So what I'll now do is go through, so I think I've sort of said it and demonstrated a few times that we can deal with different samples. At the moment, we're opening up a window and we're looking at those peaks. So we open up a window and then we find the peak through the Julie software, and then through the calibration we turn that into final concentration. And because we know the dilution factor, we also multiply the number by the dilution factor as well. But what I've just said is, in the end, Sense It All is a way of getting raw signal. Then analyzing the raw signal is actually really done through Julie. And Julie is highly configurable by you. And it doesn't always have to be Zimmer & Peacock in order to do this. So it's a very powerful and actually more flexible platform than people otherwise think. I think we sort of promote this really as a developer's system in some ways, because then you can understand it as a developer, and especially if you've got enough scientific background, you can actually really tweak this to make it work in your final application. Question number 2, I got contacted by a reseller. They sent me this image and said that the customer wants to make a microfluidic sweat sensor for potassium. So we do have a potassium sensor at Zimmer & Peacock. I think this is one of our longest running sensors that we've had is potassium. We have the microfluidics, we have the electronics. This electronics will appear later on today, because there's a few people asking about pH sensors. So we do have a set of electronics. We do have test solutions, which you'll always need, and also a rinse solution as well. So if you're looking to make a wearable potassium sensor and you want to go from 0 to 1 really quickly, then the 1, 2, 3, 4, 5 items here will basically do it, and you will actually have yourself a prototype really quickly. Question number 3, we used to do a Potentiostat called AnaPot. Now we've replaced that, where we're replacing that Potentiostat with Sense It All. The big difference between Sense It All and AnaPot is, the biggest problem I see with Potentiostats today is potentiostats today are truly potentiostats. People use them at universities, and they really, really hold back the innovation because they're potentiostats. They're meant to do lab experiments, whereas we've got this, potentiostat, and because of the, because we're of our sort of, I don't know, maybe our very commercial kind of perspective, this, I can use it to measure lead, I can use it to measure chili, but actually through its QR codes, I can do, it also just runs as a normal potentiostat as well. I could do amperometry, open circuit potentiometry, impedance spectroscopy, linear sweep voltammetry, cyclovoltammetry, and square wave voltammetry. It just uses different QR codes to open up those different assays. So I've just turned it into square wave voltammetry. It's in Bluetooth connection with my device, and I can make the device do all these various assays. What I'm now going to do is go back to the question. So AnaPot is in the same lineage as many potentiostats that you're used to. The companies developing in them and the people that use them, it keeps all the technology at technology readiness level number 3. But if you want to make an impact, for example, you really want to measure lead in well water in Bangladesh, then I think the Sense It All platform, and I'm biased of course, is the right platform for you, because it can both do the fundamental science, but it can also get out the lab quite readily as well. So I'm very delighted that this is question number 4, somebody has some pH sensors from us, and they want to know about electronics to run these. So just FYI, I know why they ask about the impedance, because if you're going to make basically a potentiometer, they want to measure potential, the units of which are voltage, of course. They want to know about impedance. Just FYI, the impedance within the device is actually quite low. This is kind of ohmic kind of impedance. I was measuring one of our silver chloride tracks the other day, and I think I got like 0.8 ohms or something. I did that on a digital voltmeter. Yeah, just FYI. I mean, if you're wondering about the impedance of devices, get a digital voltmeter out. That's what I did. I put one down there. I made a contact down there, and I made a contact up here. I think it's slightly higher on the pH sensing electrode, but not significant. It certainly did not get into any kind of hundreds of ohms place. The biggest impedance that you have was actually through the solution itself. So it's very hard for me to actually answer the question, what is the impedance of that pH sensor? Because the question really is what's the impedance of your solution? Because your solution, if you're DI water, I think the pH of deionized water is, I think, like 18 not the pH, I should say the conductivity is very low. I don't know why I'm saying pH then, but the conductivity of deionized water is very low, very high impedance. The pH of seawater, which is high in sodium chloride, is much lower. It's hard for me to answer, but I find with most buffers, or most solutions, like when I say buffer, phosphate buffer solution, maybe blood or something like that, you may find that the impedance is about 500 ohms. But generally, it's actually hard for me to say because I don't absolutely know your solution, but I suspect that you're using buffers, so I suspect it'd be in the range of about 500 ohms. We do have circuits to measure these sensors. I have linked to those circuits here, and if you're at university, I can absolutely appreciate that people at university will want to develop their own electronics. The value in developing electronics for yourself is only because you're at university and you should, learn your science and your engineering. But if you're in, let's say, the commercial world, there's very little value these days. But at ZP, we do link. We do not support any of these buttons or links. It's just a free service that we put out there that you can find some open source potentiostats linked in that link there. But the quick answer to your question is that the highest impedance is actually through the solution that you put on that sensor. I don't know what your solution is. I suspect it'll be a buffer, and it may be in the range of about 500 ohms. Question number 5, I mentioned earlier on that if people have got, unfortunately, if people have got a sexual disease, you can actually end up with several sexual diseases. It's just a pattern of the way of people's behaviour. and we are able to, be part of the development of ST biosensors, sexually transmitted disease biosensors. We have the sensor or Potentiostat. If people, which can actually do all these amperometries, these open circuit potentiometries, EIS, linear sweep, cyclovoltammetry, square wave voltammetry, which is kind of the kind of techniques that you would end up using as part of functionalizing or as part of testing for sexually transmitted diseases. We have a whole bunch of screen printed electrodes. The good thing about the ZP screen printed electrodes is actually we use these in, we are ISO 13485, so we're certified for the contract development, contract manufacturing of electrochemical biosensors, and we actually use them in our own, and I say our clients' developments. These people were interested in particular in doing multi-analyte at the same time, or multi-infections at the same time, so we do actually have quite a lot of experience of taking one sample and dividing it over several targets, let's say, so you could do 3 STs at the same time. I'm no great expert on it. I'm just thinking chlamydia, gonorrhea, HIV, for example. At least theoretically, ZP does actually have the capability of doing multi-analyte, and so we do have programs at the moment where we are helping people with 1, 2, or 3 assays in parallel. We're also working on doing 6 for particular clients. We will not be selling these Potentiostats, which can do 1 to 6 on the website anytime in the short term. They will be only available to well-funded clients who are really engaged with ZP on sort of quite large programs. Question number 6, let me read it first of all. Oh yeah, this is an interesting one. Right, so at Zimmer & Peacock we make a very unique kind of pH sensor which you can use with our single purpose biosensor circuit. And if you're going to put pharmaceuticals across it, there is especially if those pharmaceuticals are consequently going to be infused or injected into somebody, there's a risk that the material is slightly extracted. And I know I said this at the beginning, and I'll say it again now. Making sure that something is safe is one of the most costly parts of doing medical diagnostics. I think sometimes people think medical diagnostics and medical device development is about functionality, which is true, but actually it's really a lot around about safety and risk assessment. So I actually I got an AI to partly help me, because I just asked it what's the excipients in pharmaceuticals, and it came back with some of these sugars, gelatin, and then when it started hitting things like PVP, polyvinyl pyrrolidone, I can see that as being a very good solubilizer of materials, and polyethylene glycol, PEG, was also a good solubilizer of materials. But then the AI didn't actually pick up phenol and cresol, so I added phenol and cresols myself. The reason I did this is to say every formulation of a drug will have slightly different excipients. So if you're passing a drug with its unique formulation over the top of a pH sensor from Zimmer & Peacock, you will have to do a risk assessment on that, and you will have to genuinely have actually done the work, and actually done a study where you actually look for the extractants. So at ZP, it's not relevant to this particular conversation because this is happening at a university, but we generally actually have to do these kind of studies. There are ISO standards for this kind of work that we would follow in order to show whether or not material is extracted in a particular solution. I've illustrated this a little bit more here, where I just kind of pretended that there's some extractable which has the theoretical chance of extracting, but whether it extracts or not into the solution really depends on that solution. So I cannot, and I will not make a blanket statement about whether something can be extracted from our pH sensor into a pharmaceutical, because every pharmaceutical and its associated formulation is actually quite unique. And some of those pharmaceuticals are very insoluble themselves, so they end up actually putting quite a lot of organic content in there in order to help solubilize. So you have to do that study in order to deem whether something is safe or not. So lead detections in, so we only do a dilution in order to make that lead sensor as generic as possible. I would even suggest that it's so generic at this point you could theoretically do mine, brackish, well water, seawater, fresh water. I dare say blood, but it depends on the limit of detection required for blood. That's the only reason we do it. And you're perfectly welcome to start hacking into the system, or paying ZP to make it sort of more specific to a particular sample type. But for example, the way I sort of vision things is, if you're selling a lead sensor into the testing of fresh water, it would have a certain QR code associated with it and a certain workflow. If you were sending a lead sensor into mine tailings water, it would have a certain workflow and a different QR code associated with it. Potassium detection in sweat, we do have all the technologies required, electronics, sensors, microfluidics, test solutions, and rinse solution. The AnaPot is the same, is kind of coming from the same place that many potentiostats on the market, and the Sensi-All potentiostat is just a very different mindset of let's not lock this science up in the lab, let's actually get it out. pH sensors and electronics, I have definitely given you a link to some open source potentiostats. I cannot recommend them, I cannot support them, but I definitely have given you a link, and I've also given you an indication that the impedance associated with these kind of pH sensors, or pH sensors I should say, in this kind of form factor are actually quite low compared to the sort of standard glass type pH sensors you would otherwise find in the lab. And the biggest source of the pH is actually not the pH, the conductivity or the impedance is actually the solution itself. STs, doing multi analyte STs is really no problems, but let's say you were trying to do 3 or 4 or 5 assays. You've literally got to raise, you can't do 3 or 4 or 5 assays at a low cost. You really do have to be quite seriously funded, at least 10 to 20 million US dollars to do this kind of work. Measuring the pH of pharmaceuticals is simple in itself. Different pharmaceuticals have different formulations. The less soluble the pharmaceutical that you're interested in testing, then the more likely it is to have organic excipients in it. The more likely you are to have organic excipients, then the more likely you are to be able to extract materials off a pH sensor, but you generally have to do the work. I can't advise you, because it's like advising on something that you only know, you don't know enough in order to actually advise on that. So I just want to say thank you very much. I apologize for the sound quality, I apologize for the internet, I apologize that this is recorded, but as I say, I spent 20 hours yesterday traveling to here, doing these slides at the same time, and at the end of it, pretty poor internet connection. But if you've got any questions, don't hesitate to reach out to us. Okay, thanks very much.